Welcome back one more time. We're doing the Gaussian mixture model with expectation maximization. And we were just thinking about the interpretation of these conditional probabilities here. So it was the conditional probability that z equals ek given x. And so people sometimes refer to this as the responsibility, or more precisely, the responsibility taken by the kth component in the mixture. And so if you think about sort of this example, if x was here, then the responsibility, the probability of this guy, well, I mean, it might not be intuitive. It's probably intuitively clear, but to be rigorous, you would have to check the formula. But it's going to be higher for this one. I mean, assuming it depends on what these mixing components are, I guess also. But if these mixing components are say equal, then it looks like it's going to be higher for this one. So this guy is going to take more responsibility for this point than this one. So if you think by analogy with k-means was taking a hard assignment of a point to one of the clusters, and here it's sort of a soft assignment. It's a certain responsibility being taken by this guy for this point, and some responsibility, but less responsibility taken by the other guy. Okay, so that was just the sort of intuition, and way back down here, we are computing the update formulas for EM, and we've got one more to do, and it is this matrix one. So this is our last part of the sufficient statistics. It's the sum over I zik xi transpose. So part 3, sum over I zik xi transpose. And those should be random variables. Let me make that clear. zik xi transpose. Given x equals little x equals the expectation. This is under theta 0. This is under theta. Same thing. Random z ik xi transpose. Random. And let's do this one again. This one's probably, I think, going to be easier, just like before. And yes, it is. So the expectation moves through. And just like before, in the case of the vector valued 1, we just get the conditional expectation of zik given x. These x's come out, and we just get the sum over I rik xi transpose. The random x's get set to the random xi's get set to little xi because of the conditioning. So that one's easy. And how about this one? Well, we're going to take a similar approach to before. We did this we broke the expectation up into a expectation of a conditional expectation. Oh, we already have the sum. Z ik xi transpose. Okay. Oh, sorry. Given z ik. And now let's do the same sort of thing as we did here. Just like before here, when we only have to worry about the case when zik equals 1, because when it's 0, this is just 0. So let's think about that one. So let's think about this conditional expectation when zik equals 1. Well, when it's 1, we can just forget about this. This just is 1. And so what is the conditional expectation, or what is the conditional expectation of this thing? This xi transpose. How the heck are we going to what are we going to do for that? Well, if you know your covariance matrices, then you recognize, so this is an aside. Let me make just an aside here. For any random vector say y, all right, we're not using y for anything, the covariance matrix of y equals the expected value of y transpose minus the expected value of y times the expected value of y transpose. And this is just follows by the definition of the covariance matrix. If you multiply these out, and the definition of covariance, multiply these out, and then element-wise, you get the right thing. So that's a little distracting there. So this thing, so we just need to think about what is the covariance matrix for the conditional distribution given zik equals 1. The conditional distribution on xi. And then we will just be able to, we solve for this, it'll just be the covariance matrix plus the mean times the mean transpose. So what is the conditional distribution? Well, that's just exactly, remember, go back up here, back up to our model one more time. That's just, again, that's just this normal distribution. Given that zik equals 1, then xi is normally distributed with mean mu k and covariance ck. So the covariance matrix is ck and the mean is mu k. So one more time. I'm almost out of space. This thing equals the covariance matrix ck plus, remember it's plus because we move this over, mu k transpose. This conditional distribution. All right, so let's use that now. See if we can use that. Here, this was, let me just, let's continue this over here. This equals the sum over I. Remember when zik was 0, it just dropped out. So it's the probability that zik equals 1. I'll put that again, under theta, times this conditional expectation given zik equals 1. And that we found was this thing, ck plus mu k transpose. And this, just like before, this was alpha k, where alpha, it was the alpha for this theta. So what do we get? We get the I just makes an n, so we get n alpha k, or the sum makes an n alpha k, ck plus mu k transpose. And we would like to solve this for ck. So first let's do the trick again of getting rid of alpha k. Alpha k was, just like before, alpha k was nk over n. So this becomes nk times ck plus mu k transpose. Losing my voice. And now we'd like to solve this for ck. So let's do that. And I think we have just about got it. Ck equals, we move the nk over, and then move the mu k transpose over. We get 1 over nk, sum over I, rik, xi transpose, minus mu k transpose. And that, and maybe just to be clear here, this is separate from that. And that is our update formula for the covariance matrix. And so we've got, since we already have, we have mu k, we've already solved for mu k here using some of the earlier conditions. Then we can just plug in whatever we get for mu k into this equation here. And we know rk, of course we know the x's also. And we know nk. Nk was the sum of the rik's over I. All right, so this is our update. So maybe just to recap here, to show that this is what we wanted. for EM, for the this formulation of EM for exponential families, we wanted to solve this equation, or rather this set of equations. This was an equation for each j, and we wanted to simultaneously solve that set of equations for theta, assuming that we know theta 0. And that would give us our update, because then we would have, that would be like, if that was theta 0, this would be theta 1, and then we would put theta 1, and we would get theta 2, and we would get theta 3, and so on. And so that's exactly what we did. We wrote down these equations over each j. We sort of grouped them together into groups of j that were convenient to work with. And then we solved those equations. We did it. We got theta, right? Because theta was alpha, all the mu's, and it was all the c's. And we got down here, we got all the alphas. This is just, alpha was just alpha 1 up to alpha m. So we got all the alphas, right? This was the definition of nk here. And this was, maybe I'll put this whole thing here. We had all together this was the definition of rk was this, or rik was this, and the definition of nk was this. Definition. So we got all the alphas, we got all the mu's, and we got all the c's, all the covariance matrices. So we've got it. So that's it. That's EM for the Gaussian mixture model. And it's so, I mean, it was some work to derive it, but this is just very easy to implement, because all you do is you just iteratively solve these equations. And once you've solved them for one step, the only thing you have to really, I mean, you have to update the RIKs to use in the next step. But that's easy, because that was just this calculation way back up here. This was the RIK thing here. This would be like RIK if this was XI. And that's easy to compute. You can just analytically compute that. Then so you get your RIKs for the next step, and you're off to the races. All right, so that's EM for the Gaussian mixture model. And let me make one remark here. One thing that might be a little bit is a little bit subtle about this is that these alphas, I said when we were deriving this formulation of EM, this formulation, that the theta couldn't have any constraints, sort of. And these alphas have to sum to 1. These define a PMF, right? And so that's a constraint that you would think that we would have to take into account when we were doing the maximization step in some sense. But it turns out that we did take them into account in an implicit way. So in a sort of very subtle way, that constraint was already incorporated into the derivation of this result. And that won't always be the case, but in this case it was. And the reason is because that constraint was implicitly included in the normalization constant. So here, this was right. This is good. This was the form of the exponential family, and theta. We didn't, when we did the maximization of this originally, we didn't have a constrained maximization. But it turns out that the constant here, in this case, for these alpha k's, this constant acted as a Lagrange multiplier in that maximization. The normalization constant acted as a Lagrange multiplier, and that's why it actually was a constrained maximization. And that's why it worked in this special case. But this is, I want to emphasize, a special case, and that doesn't necessarily always happen. Okay, so that's it. So that's EM for the Gaussian mixture model. We've got it, and I hope you found that interesting to see an alternate way to derive this.